Hello everyone. Today we are going to be looking at juice components with some must additions math thrown in there for fun. This presentation is meant for students at the Institute for Enology and Viticulture. However, students in other wine study fields may find it interesting. So sorry everyone, in this Canada Day week, this is going to be the most difficult lecture we've had to date. So this is the introduction to a topic that you're going to see over and over again at the Institute. So I want a little bit of this to absorb, but don't worry, you're going to learn this over and over again. So to start out, we have our grape berry structure. And we have the outside and the skin, or the peripheral zone, where there's quite a bit of flavor and also tannin. If we're dealing with a red grape, that tannin can be extracted into the wine. If we're dealing with a white, we might be dealing with concerns of tannin extraction into the juice due to press style. The harder we press the fruit or the more tumbles we do during the pressing process, the more tannin we can get leach into our white juices. An interesting fact here, closer to the center of the berry, in this central zone here, there's quite a bit of acid which is held close to the seed. And what we've observed over at the college is that when we hard press certain varieties in certain years, we can get more extraction of acids just because that acid is being held closer to the seed. So today we're going to look at sugars, and we're going to talk a little bit about how we analyze or estimate sugars in our musts through hydrometer, refractometer, densitometer, or direct sugar measurement. We're going to look at acids. So we're going to look at pH, titratable acidity, and direct acid measurement. We're going to look at nitrogen-containing compounds, including alpha amino compounds and ammonia. And then we're going to take a look at potassium and see how it relates to some different components of the wine. And then we're going to go over some ETS reports. And I'm going to show you how I can take a look at chem data and start seeing potential problems so that we can remediate them, or not remediate, I should say, confront those problems up front so they don't require remediation later. So this is essentially what we're going to be looking at here. So this is a juice panel from the 2019 Stony Vine Syrah. And ignore the little green part. That is our phenolic data from the grape berries, and we're going to dive into that in future lectures. But just get used to seeing titratable acidity, pH, L-malic, tartaric, Brix, glucose plus fructose, ammonia, alpha amino compounds, yeast assimilable nitrogen, and potassium. Going to see those words a lot. So starting out with our sugars. These are mainly in the pulp of the berry, like you saw in that previous diagram, and as you know, these increase during ripening. And in the United States, we express these sugars as Brix. So 1 degree Brix is 1% sugar, or 10 grams per liter. And Brix is a measure of total soluble solids, so it's actually not a direct look at how much sugar is present in the grape. And we use Brix, which is actually just a look at density, or total soluble solids, because when we get over about 18 degrees Brix, what we're seeing is that the vast majority of things that are providing mass or soluble solids in the liquid are sugars. So it provides us a pretty decent estimate of how much sugar is in there. So why are we looking at sugars? Mainly because it's a prediction of alcohol in our wines. So approximately 1 degree Brix is 0.6% alcohol by volume. But there are many factors that influence sugar to ethanol conversion, and we'll talk about that later, but it's mainly related to yeast stress. And yeast do get pretty stressed. So if we're above 25 degrees Brix, this can be a difficult situation for yeast, and we have to figure out how to support them more. What they're experiencing is osmotic stress. Basically, there's too much sugar surrounding their bodies and not enough water, and what ends up happening is water wants to go out of the yeast cell and into the juice. And this sucks the water right out of the yeast bodies and causes them to be very stressed out. And then additionally, once we're approaching the end of the ferment, we're also having very elevated ethanol levels, which are toxic to the yeast cells. So we're getting a twofer here of stress on the front end because of too much sugar and stress on the back end because of too much ethanol. So what we have to do as winemakers is really figure out how to support our yeast during the fermentation process, and that's a discussion for another time. So here are the tools that we use when we're measuring density and inferring sugar from that density. We can have a hydrometer, which is what we have right here. So these are based on specific gravity, and we drop this hydrometer into a tube filled with liquid, and the higher it floats, the more dense the solution is, so therefore the higher sugar. We can also use a refractometer, and that's what these guys are right here. So this here is what the refractometer tool looks like, and then this guy up in the corner here is what we see when we look into the refractometer. And this operates on the principle of refractive index. So this is actually the same principle as to why diamonds sparkle. So what we have is a solution of sugar, and as the sugar or the density of that solution changes, so does the refractive index. So light refracts differently at different densities. And what we do here is we just place a little drop of liquid on the slide there and close it, and then look in, and what we'll see is an angle of refraction, and it's giving us a density of the solution. This does not work during fermentation because now we have ethanol in the mix, which decreases the density of the solution, and it really just messes it up. So this is a great tool for the vineyard, but not a good tool for the winery. And here we have my favorite thing, the densitometer. So this is a very accurate tool, and it's your harvest best friend because you can go through and measure multiple lots really fast. And this works on the principle of oscillation. So we have this little U-shaped tube right here. So what we do is we suck the liquid up into the tube, and then it goes into that U-shaped tube there. And then this tube is forced into vibration, and the frequency at which it vibrates is related to the density of the liquid inside that tube. So this is a multi-purpose tool. Like many things that we have in the wine industry, it wasn't originally produced for the wine industry because there's not a lot of money in producing equipment for the wine industry. There's more money in producing equipment for the oil and gas industry or the dairy industry. So these tools can measure alcohol in distillates, fat in milk. It can also measure crude oil. Basically, it can really measure the density of anything if you give it proper calibration. So we actually use this tool on some distillates in our winery as well. It can work on glycol, and what we can do is also figure out the alcohol percentage in distillate spirits like brandy. So we need about 70% ethanol to get a sanitizing solution for our winery. So to ensure that we're getting to 70%, we can measure that in the densitometer. The best way to look at your sugars in juice is actually direct sugar measurement, because none of those methods that I mentioned earlier actually measure sugar concentration. What they are doing is taking a look at density, and then we can infer the sugar concentration based on that, but none of them are actually measuring sugar. So direct sugar measurements take a look at glucose and fructose concentration, which are the main sugars in the grape produced by vine photosynthesis. And they're also the main sugars that are going to be consumed by our yeast and converted into alcohol. So if you actually have a direct sugar measurement, that's the best value to use for calculating your alcohol concentration. So when I take a look at ETS reports, we do have a Brix value on there. But what I end up doing is taking a look at the glue-free levels, which are direct sugar measurements, and then dividing it by 10 to get an actual Brix, and then multiplying it by 0.6 to get a potential alcohol level. So this is a really nice value to have pre-fermentation, but this is an essential value to have post-fermentation, because all those tools that we mentioned before are not going to give us an indication of dryness. The only way to actually determine if a wine is dry is by doing a direct sugar measurement. So you can't just see a flatlining level on your densitometer or your hydrometer and say, yep, we're dry. You really do need to send your wine in for a proper test. Moving into acids. So there are two major acids present in our juices. It's tartaric and malic. And tartaric has 2 protons and occurs naturally in grapes, as you know, and it's also the strongest acid that we have present in grapes. So all the acids that we have are organic, so they're not technically strong, they're weak carboxylic acids, but this tartaric is still the strongest of all of those acids present. We also have malic. And this is going to be declining post-veraison, and it's common to see a value higher in tartaric than malic when we take a look at our juices. There's also citric and lactic acid that can be present. Citric occurs naturally in grapes, however, at very, very low levels, so it's not a significant contributor to acidity at all. And in general, if you actually have a wine with significant citric acid present, it's because it was added intentionally or might be a residue from cleaning solutions or sanitizing solutions, excuse me. And then we also have lactic acid. So this is produced from malic during malolactic fermentation. And if it's present in your juice, it's an indication that we might have had some vineyard rot because this is not present in clean juice. So these acids, what they do in juice and wine is they donate protons into solution, which lowers the pH of the solution. And these acids have 3 major functions. Flavor, because the tartness or sourness of a wine is a really essential component of the flavor, especially important for white wines and rosés. They also help with microbiological stability because they're forcing down the pH. So spoilage microbes don't like high acidity or low pH. So these acids are really helpful. And this also helps us select for Saccharomyces cerevisiae. So an example of that would be if we had a wine closer to pH 3.2, Saccharomyces cerevisiae would have a competitive advantage because spoilage microbes don't really want to grow at that pH. But if we have a flabbier or a higher pH wine closer to pH 4, there's a lot of microbiological competition out there against our Saccharomyces. And additionally, acids can help with chemical efficacies. So SO2 is most effective at lower pH levels. So the acids are actually contributing to the SO2 effectiveness, and that in turn is also acting as a suppressant on microbial growth. So there's a couple different ways of looking at acids. The 2 main ways are pH and titratable acidity. So pH is a reflection of the concentration of free hydrogen ions in a solution. It's not a direct concentration value. So it's the negative log of the hydrogen ion concentration. And it's on a log scale. So a wine at pH 3 has 10 times more protons than a wine at pH 4. And low values generally mean greater microbial stability and SO2 efficacy, like I said on the previous slide. Titratable acidity reflects the concentration of protons that are titratable in the wine. So that means the protons that are free, but also the protons that are still attached to acid skeletons. So the free protons and the ones that are still attached. And this has a correlation to sensory, and it gives us a common language to describe the acidity of wines. So we use this really commonly when we're thinking about acid additions in wines. If you're at the blend table, for example, you can communicate with your peers there and say, well, we have this acid trial. We've got a TA of 5.5, 5.6, 5.7 grams a liter. Then you can say, well, I like 5.7, and your peer says, well, I like 5.5. So it gives us this important common language to describe the sourness of the wine. But titratable acidity doesn't have a correlation to microbiology or chemistry. Titratable acidity and pH are not directly related, but they are loosely related. So a higher titratable acidity value generally means a lower pH, but this relationship isn't perfect, and we'll talk a little bit about that in EV204 next year. How do we measure these things? So pH is really easy. You stick a pH probe in the wine. All you got to do is calibrate it and keep it clean. For titratable acidity, we perform a titration. So we add sodium hydroxide to a wine while measuring the pH. And the sodium hydroxide neutralizes the acid that's present in the wine. And then what ends up happening is those acid skeletons that still have the H or the protons attached to them give up those protons and throw them into solution. And then they're gobbled up by the sodium hydroxide again. So the amount of sodium hydroxide that we add to neutralize all the acid is proportional to the amount of acid present. And what we can do is then do a simple little math calculation to figure out how many titratable protons were in the wine. And then we can determine how many acid molecules were present. And just like glucose and fructose, direct measurement is my favorite. So this measures the acid species directly. And it's not a combination estimate like titratable acidity is. And we will go into the shortcomings of titratable acidity a little bit later in EV204. But direct measurement is a really powerful tool because it actually does give us hard values on the tartaric and malic acid concentrations. And this is important because we can see which acids are actually really contributing to our acidity. And these are important when thinking about cold stabilization because we always lose tartaric acid when we cold stabilize. So we can anticipate some problems there if we know the concentration of tartaric. We can also see where things are going to shift during malolactic because we're going to lose that malic acid during malolactic fermentation. And it's really helpful to see how much tartaric and malic we have when making acidification or deacidification decisions. And here we have an example from our 2019 Estate Barbera. So this juice panel was pulled on October 14, 2019 when we harvested the fruit, and I can see a few red flags here. Mainly this titratable acidity level right here at 10 grams a liter. So if we're looking at that with no additional data, that's a really concerning number. 10 grams a liter is very, very high, and there's only 2 finished wines that I've actually seen that have had a TA of 10. One was a Mosel Riesling and the other was a Champagne. So this is a really sour value on paper and would be concerning in a dry red wine like Barbera. And we also have quite a bit of acid when we look at the specific acids as well. So close to 5 grams of malic, which is quite a bit, and 6.8 grams of tartaric. So this definitely legitimately has acid. Some other considerations here. Looking at this little potassium number here, what we're seeing is that we have something that can bind to our tartaric a bit later on. So what I'm anticipating actually is that we're going to lose a bit of tartaric thanks to that potassium. So here's the chem panel from March 17th, 2020. So we did lose titratable acidity during primary fermentation. Look how we shifted from a value of 10 down to a value of 7.5. This is mainly due to loss of malic acid during malolactic fermentation. 7.5 grams a liter is still a really tart value. 339, when I look at that pH, that's a white wine pH. That's like a Sauv Blanc pH. So this is still a very tart wine. And we did see a shift for sure, but I would be cautious on wines like these if I was deacidifying. For example, if this wine had lower levels of tartaric and we decided just to chemically deacidify it, we could have blown out all of our acid because we lost the malic during malolactic fermentation, and then we would have taken away quite a bit of our tartaric thanks to chemical deacidification. This wine actually still is a candidate for a bicarbonate add later on. That's something for us to discuss when we're getting your blends figured out. But I would like to retaste this wine with the production group and see if we want to make some tweaks, because Barbera is meant to be high in acid, but this is really high in acid. So let's do a little bit of acid adjustment math. So thinking almost like the reverse of that Barbera. For most red wines that we end up making at the college, we are doing a small amount of acid adjustment. So the acid adjustment math is we're figuring out what our target acid is and subtracting our current acid, so we figure out basically how much we have to add in grams a liter and then multiply it by a wine volume. So let's imagine that we have a current acid of 5 grams a liter and we want to get to 5.5 grams a liter. Let's make it easy on ourselves. Let's imagine that we have 1,000 liters. So then 5.5 minus 5 is 0.5 gram per liter times 1,000 liters equals 500 grams. There we go. We would add 500 grams of tartaric. Wow, my writing is bad when I'm writing on my tablet. So we would add 500 grams of tartaric acid into this wine to get a 0.5 gram a liter bump in titratable acidity. And for some fun, let's take a look at pH ranges in different varieties. So this is a little slide that I created using some data from Global Wines. And we have a pH range here ranging from 2.9 to 4.2. So that's what we're seeing in wines. Way down at the bottom, we're seeing sparkling wines and Rieslings. And way up at the top, interestingly enough, we're seeing Syrah. Syrah has the widest range of any variety that I've seen because we have wines from Australia that can have very moderate pHs and wines from the Rocks district of Milton Freewater which have very high pHs. And our other varieties are falling somewhere in the middle. Moving on to nitrogen, and specifically yeast assimilable nitrogen. So this is our yeast food, and we have two components of nitrogen that we look at in our juices, and that is alpha amino compounds or amino acids and ammonia. So these amino acids are the building blocks of cell components, and they're very important because this is where actual nutrition in the yeast comes from. So we measure this via enzymatic analysis, and for ammonia, you can measure that with a probe. Ammonia is easy to add via DAP, and it provides nutrition with, energy with minimal nutrition. So it's sort of like a candy. It's giving you that sugar, if we're thinking about, snacks for people, but it's not providing us with really good nutrition. So our nitrogen levels range from 30 through 400 milligrams a liter in in juices. And supposedly we need 320 milligrams a liter to complete an optimal fermentation. But as a caveat to that, I will say that I've had my mind consistently changed from 10 vintages of making wine, comparing what I observe to what I've read in textbooks. And I'll say that some ferments actually need significantly less nitrogen. And I think it may just have to do with how well the yeast are adapted to the situation. What we're seeing is that we're actually having successful native fermentations with limited levels of nitrogen. But under usual or normal circumstances, what we end up doing is supplementing with diammonium phosphate, aka DAP, or other complex nutrients to bump up our nitrogen levels. Nitrogen can be a really tough issue in Washington. Our yans are notoriously trash. So here's a little example. Here's some anecdotal things. Deciding to add DAP in 2 different wines. So looking at our 2019 Mourvèdre from Stony Vine Vineyard, we see really nice yans from our fruit sources in the rocks. So this had 224 milligrams a liter of yeast assimilable nitrogen and 220 grams a liter of glue-frue, or an actual Brix of 22. So this is a moderate Brix ferment with really nice high yan. So we didn't need to add any DAP. But for our Syrah from Cockburn Vineyard, we have a significantly higher glucose fructose level of 268 or 26.8 degrees Brix. We had a yan of 41, which is not going to get us far. So high Brix, low yan means definite DAP add, or we're going to stick this ferment quickly. So we added 900 grams of DAP, which came out to the equivalent of about 165 milligrams a liter of yan that we added. So let's play around with a little bit of nitrogen math. And I'm just going to open up my calculator here on my phone because I can't do it without a calculator. So our DAP add is going to be our target yan minus our actual yan times our liquid volume. And we now have a new player here, and this is 0.22 because when we add DAP, 22% of the DAP is actually the usable nitrogen. So that's where that factor comes from. So let's imagine that we have a target value, let's do 250. And our actual yan is 50, which is unfortunately common here in Washington. And make it easier for ourselves again, let's say that we have 1,000 liters. So then 250 minus 50, that'll be 200 milligrams per liter times 1,000 liters, all over 0.22. Calculator says 200 times 1,000 divided by 0.22. We're going to get a big number. All right, so it's 909,090 milligrams, or we can just cross that out and say it's 909 grams. Moving on to potassium. So potassium is imported into the grape berry cell during ripening, and 30 to 40% of this potassium is actually in the berry skin. So when we press our whites harder or have a skin soak on rosés or red wines or orange wines, what we're seeing is that we're getting increased potassium, which actually contributes to a pH increase in the finished wine. So this is a more advanced topic that we'll discuss next year. But basically, the longer you have your white wine in the press and the longer that you actually have contact in between your juice and your skins on a white wine, you're going to get a higher pH level. And I actually do know some wineries where they do their press cuts based on pH as opposed to flavor. So what you need to know, like I said, whites, the long press time is going to increase your pH as it's extracted out of the skins. And for reds, we're going to get that potassium extraction during the maceration process. So we're going to see more and more potassium extracted in during more and more maceration. So extended macerations will have the highest amount. And potassium needs to be removed during aging. And we can do this through the traditional cold stabilization process, which involves binding potassium and tartaric acid to form potassium bitartrate, so that this doesn't happen in bottle when the product is on the shelves. So as a bonus kind of portion here, we're going to go into a deep dive, and I'm just going to talk through some decision making based on chemistry. Taking a look at our 2019 Sauvignon Blanc. So I'm putting some eyeballs on this report here, seeing if I see any red flags. TA looks good, 5.7. pH is actually a little surprisingly high, but I love that 6.6 grams a liter tartaric. That's a fresh looking number to me, and close to 2.5 grams a liter of malic, none of which is going to go away because we don't put this wine through malolactic fermentation. Nice moderate Brix. Not so good on the yan here. This is not enough to get us through, so we're going to have to add some DAP to this wine, or juice I should say. So yeah, basically I'm really happy with these numbers. We're not going to get an elevated finished alcohol here because we have 23.7 actual degrees Brix. Nice looking fresh acids, and we do have a yan that requires a DAP add. Here we have some remediation that needs to occur. So muscats are notoriously flabby. Muscat just doesn't hold acidity well from the vineyard. So this isn't specific to this growing season or this vineyard. Muscats just have lower acid than Sauvignon Blancs, which we would compare it to in the previous slide. So this may be a little bit flabby here because I'm seeing a tartaric acid of 5.7. This is actually pretty good looking. The tartaric is a gram a liter lower than the Sauv Blanc, and it's not like we want this muscat to taste like the Sauv Blanc, but it's still quite a bit lower. I love this friggin' muscat, man. Full flavor at 20 degrees Brix. So good. So the alcohol levels are never elevated in these wines, and they're especially not elevated because we don't ferment this all the way to dryness. The wine does have residual sugar left over. And so what we did on this wine here was we added 1.5 kilograms of malic to pop up some of the freshness on that acidity. I really like malic acid for additions on white wines because the human palate, it views it as a little bit more of a natural flavor. Tartaric acid really only exists in grapes and tamarind, but malic acid is present in so many different fruits. Probably the most common one you would think of is green apples. So if you're going to be doing an acid add on a white, I like either malic or a little mix of malic and tartaric because it helps it blend in a little bit better than just a pure tartaric acid add. So this wine had approximately 0.8 grams a liter of acid added to it. And the Yan is better than the Sauv Blanc by quite a bit, but it's still too low for a fast and pristinely clean ferment because if you remember, this wine goes to bottle in October, so we have approximately 1 month to get this thing fully processed, wrapped, filtered, CMC added for cold stability, and then sterile filter on the bottling line. So that's really fast, so we need our ferment to be fast as well. This one, we're not looking to have a long, slow ferment like we would on maybe say a Chardonnay in barrel. This one has to rip and it has to be clean. So DAP is necessary. All right, here is where things go off the rails. Tempranillo for us has always been a little bit of a mess. So let's go down the line here. TA of 5.7, that isn't bad, but that's a number that we would expect more to see in a finished wine. What I'm seeing here is pretty lousy levels of tartaric acid and quite a bit of malic acid, which is going to go away. And I'm seeing a very concerning pH here. 3.69 is high. So when we have values over 3.65, we are in a situation where when we have malolactic fermentation and cold stabilization, the pH always shifts up if it's over 3.65. So what I'm seeing here is a low acid situation in the first place, and then I'm expecting that this value is going to pop up even higher. And hoo boy, we got a lot of sugar here, so 27.7 degrees Brix. So we are expecting a finished alcohol in this of 16.6, and we're not going to let that happen for many reasons. One is we don't want that level of alcohol, and two, we're probably going to stick that ferment if we're approaching 16.6 because the yeast are not going to want to finish. So that says to me you need to add water. And then we take a look at our Yan here. It's not great, so we're going to need to add DAP as well. So basically, we need to start cooking here. We need to start adding ingredients. And here is where we landed. So this is data from March 9th. And back to a little bit of normalcy here. So taking a look at our 2019 Cab Sauv. Let's take a look here. Ooh, nice low pH. TA is very good. We might need to add a touch of acid just because we're expecting to lose some of it during the fermentation process. Like what I'm seeing here with potassium of 1450, that's 1.4 gram per liter. that we are going to lose because that's going to bind up with that guy there. So adding a little bit of acid here doesn't hurt us. So 27.1 degrees Brix of actual alcohol, of actual Brix. So then that converts into about 16.2% ABV. I took a look at our production record on this one, and I didn't see a water add actually. So either we converted low on the sugar to alcohol, or someone added water and didn't tell us, or someone washed that bin down with the hose real good. Almost forgot about Yan here. Fruit tastes great. Yan is trash. We can add DAP, no problem. Advanced topic for another time, and you'll learn this in Joel's class. There is an inverse relationship between nitrogen accumulation and tannin and color development in fruit. So this fruit has absolutely gorgeous color and rich tannin, and the sacrifice that we make is that we have low Yan in the fruit. No big deal, because we can always adjust our Yans, but it's pretty close to impossible to adjust our color and tannin. So the right choices were made here in the vineyard for sure. And this is where we landed on the Cab Sauv here. So looking good. 383 is a pH. This is kind of high in the grand scheme of things, but not at all out of the norm for Walla Walla or Napa Cabs. Tartaric acid of 1.3. It's like, where did all the acid go? There's no malic. There's only 1.3 gram a liter of tartaric. It's one of the great mysteries. TA of 6.5. So tasting fresh, I think that would present to us as pretty fresh. Ethanol of 15. So pretty standard for us at College Cellars. One thing to keep our eye on in the future here is that we have 1,250 milligrams a liter of potassium. So that's 1.25 gram per liter of potassium. And I'm expecting that during the cold stabilization process, that's going to pull down some of our TA right here. So either way, though, we're in smooth sailing. This is like the opposite of what we were dealing with the Tempranillo. Not a lot of intervention required here. Basically, everything just fell in line. Alrighty, we made it to the end. Now you deserve to go relax your brain. So be like Digby. Let your mind touch the void a little bit. If you need to review, you can simply click back through this presentation. If you have questions, please email, text, whatever. I'm here. Alrighty. Cheers, friends.